Ok.
Tobias, você está me ouvindo?
Oi, bom dia. Oi, Débora.
Tudo bom? É a Patrícia, tudo bom?
É a Patrícia, como vai? Tudo bem?
A gente vai aguardar uns minutinhos, porque o pessoal está lá no hotel tendo que fazer o check-out.
Ah,
Então,
tá bom.
mais alguns minutinhos, acho uns 10 minutos, tá bom?
Ah, você que vai liderar a sessão hoje.
Eu que vou passar
Ah, que ótimo.
bastão aqui, o microfone para mim.
Tá bom,
Tá bom.
perfeito.
Então, acho que uns 10
Tá,
minutos.
eu aguardo, ok?
Tá bom.
Estou aguardando, tem problema.
So just to tell everyone, I think we are waiting 10 minutes because people are doing the checkout at the hotels.
Patrícia? Alô?
Oi, tá me ouvindo?
Oi, estou ouvindo. Patrícia, é 50 mais 10, né?
50
Só
mais
para... Tá bom,
50, 45, 50 de apresentação e aí
tá
10
ótimo,
perguntas, tá bom?
tá ótimo. Tá, obrigado.
Imagina. questions. Hi, Tobias.
Oi, oi.
So maybe we are going to start. The room is getting full, so I think we can start our section. It's okay for you?
Yes, yes, I'm ready.
Okay. So welcome back, everyone, to this last day of this nice workshop. So today, for the first talk, we are going to have Tobias Frederico from the Instituto Tecnológico de Aeronáutica here in Brazil. And he's going to talk for us about Few-bosons, limited cycles, and discrete scale symmetry in integer and non-integer dimensions. So thank you very much, Tobias, to be with us today. And you can start whenever you want. Thank you.
Okay, thank you, Patricia, for the introduction. First, I would like to thank both Arnaldo and Alex for the kind invitation and the possibility to talk online, to present the work we have been doing with many collaborators in Brazil, essentially. And what is the context of what I'm going to talk? Okay, technical problems. Okay, what's the context? Is essentially I will discuss atomic physics, cold atoms, could be applied to cold chemistry, and also to halonuclei, because this will be, I will talk about weakly bound systems, essentially, so very large compared to the range of the potentials. And everything I will talk about is thinking on low energies and therefore long wavelengths. So now, first I would like to introduce the helium-4 dimer. Here is the wave function that is actually what was measured, the density distribution as a function of the radius in angstroms units. And then the binding energy of the dimer of helium-4 is very small. No, it's 150 nanoelectron volts. And it has a very large tail. And this small bump here is just the van der Waals potential. So the wave function will stand far away of the potential. Essentially, it is very universal because it's the eigenstate of the free Hamiltonian. We can go on. This was already experimental information that was taken from the diffraction of helium-4 and trimer beams, dimer beams, and the explosion, laser explosion, that you can have the information on the momentum distribution, and from that you can have the information on the probability density, essentially. And here is the what you get from the ground state, you see in blue, and this is the distance of the helium-helium pair. So this is the trimer, helium trimer, and the distance is pretty large. You see, is of the order of 15 angstroms, the average distance that you have between the helium-4 atoms. And for the excited state is very large. No, it's 7,500, you can see here. So therefore, what reminding that the van der Waals or Lennard-Jones potential, some potential that you use to describe this trimer and dimer. So the range is of the order of the van der Waals length. That is pretty small. So this is, in that sense, we can think that the wave functions stand beyond, much beyond the potential range. Okay, so this is just a list of atoms and their van der Waals radius, and we see that they are always of the order of a couple of angstroms. No, this is the van der Waals length in units of 10 minus 2 angstroms. So we have many atoms that they interact. I mean, these are the neutral atoms with this van der Waals potential. That is indeed, if we think, I mean, on the molecules that we are going to discuss, this range is pretty small. And we can think, I mean, even these atoms can be trapped in atomic traps, and you can manipulate the scattering lengths, no, or the dimer energy, if you want, as well, with patch bar resonances. And these are, I mean, very large scattering lengths. So you can think now, if you that your scattering length is very large compared to the van der Waals length, for example. We have experiments done with cesium trimer, cesium-2, lithium-6, no, for negative scattering lengths, for positive scattering lengths. And also, there are, besides the helium trimer, there are other molecules, like you see the dimer of helium-2, lithium, helium, the dimer of helium-4, so on and so on, that are indeed weakly bound. No? And this could, one could think about if you do reactions with those molecules, this, as you have very small binding energy, remember this is 100 it's very small, the dimer energy here. And so you have to make these reactions to have a very low temperature. So this defines an ultra cold chemistry. Okay, now going to the nucleus, where you can think about this weakly bound system is close to the drip line, neutron drip line. We have many nuclei, for example, Bohromian systems, and also you could have non-Bohromian system like carbon-20. So the neutrons here, two of the neutrons, for example, are weakly bound. No, in the, of course, we have to think now on the nuclear scale. No, so this is a fraction of MeV that they are the separation energy. So these nuclei, this halo of neutrons are pretty large. So the idea here is just one scheme for lithium-11, that is the most famous Bohromian. So you have a core of lithium-9 that the size is about 3 Fermis, and the halo of the neutrons at a distance of 6 Fermis from there. So this is really a huge halo. The same you can find in carbon-22, for example. So, and then how do we think of a template of these, to understand the physics of these weakly bound systems or very large systems, and how we go from 3 to the 2 dimensions as well. So the template I want to discuss is just that. As the states are very large, much larger than the range of the interaction, essentially almost everywhere the wave function is an eigenstate of the free Hamiltonian. No? And therefore, in that sense, universal. But you need some boundary condition to fix it. No? And this, of course, will will imply the necessity to fix some scale. For example, the binding energy that gives the tail. So what we notice from this equation is that there is a scale invariant if the energy is zero, no? If we change the momentum, essentially nothing happens, no? If we think about the energy equals zero. But then the physics should be dominated, of course, besides some scales, the symmetry that you have fermion bosons, angular momentum, and of course, mass ratio. So essentially, what I'm saying about these weakly bound systems is that they are very large, and therefore we should expect a lot of model independence. So you change the potential as long as you kept fixed some, let us say, low energy information about your system. What you get should be essentially the same. And of course, the limiting case that I'm going to discuss a lot is a contact interaction. No? But then, of course, there is the question, okay, you are talking about the information you need to put or physical scale to define the system, how many? No? And what happens when we go from 3D to 2D, when we squeeze the system? Okay, just a very naive view of what's going on, for example, in a three-body system. We can imagine that two of the bodies interacts, then there is a scattered wave, that this scattered wave will come to the third particle, and so on. So essentially, in a first, if you think a first view of that, what matters is the asymptotic information that is in this scattered wave. And this essentially will be dominated by low energy S-wave information if we are at very low energies. And of course, in 3 dimensions, we can think in the scattering length. In 2 dimensions, I will think about the dimer energy that fix that. But do we need more information than that? Okay, so let us discuss this a little bit more in detail. I will look to 2 and 3 particles in 3 dimensions. So, okay, so what fixes that scattered wave is the scattering amplitude that is defined through the effective range extension of K cot delta. We have the scattering length, the effective range, and the situations we are thinking is that the scattering length is much larger than the range or the effective range of the interaction. Just now to remind, if the scattering length is positive for short-range interaction, we have a bound state pole. If it is negative, we have a virtual state that appears in the second Riemann sheet. Okay, so the ilium dimer is bound, so 150 nanoelectron volts, scattering length huge, 90 angstroms. Also with Feshbach resonance in cold atoms, we have a very large scattering length, much larger than the van der Waals length. In nuclear physics, we have the neutron-neutron virtual state. You see, this is a large energy from the point of view of atomic physics, but on the nuclear physics level, the neutron-neutron virtual state energy, or the singlet state, is very small. It's 140 kiloelectron volts. And in the nuclear scale, the scattering length, neutron-neutron scattering length, is minus 17 Fermis. Remember that the nuclear force, the range is about one Fermi. Of course, for halo nuclear, this also happens. Okay, so now what is interesting in 3 dimensions for 3 bosons? That is the Efimov effect. You have heard a lot, but what is important here for us is that The Efimov effect that was discovered in 70 in the context of nuclear physics is what? When the scattering length, this is essentially the inverse of the scattering length. So this is the region where you have a bound dimer or a weakly bound dimer, and here you have the virtual state, the negative scattering length. So when the scattering length goes to infinity, you have an infinite number of levels geometrically separated. And in the case of three identical bosons, you have the ratio between two of these energies is about 515. So it's a huge distance between. But what you see here is a discrete symmetry. No, you see the form when you move the scattering length. This form is essentially identical to that, and then they are just grayscale. And here, the Efimov state, when you move the scattering length, it just comes. This is when you increase the modulus of the scattering length. It just comes from the dimer threshold, and then here is when the scattering length is infinite, and when you still continue decreasing the modulus of the scattering length in the region of negative scattering length, the Efimov trimer disappears in the continuum. And it creates a continuum resonance. No? And this is what allowed essentially to observe it in cold atomic gases. So when you move the scattering length with a Feshbach resonance, and the trimer hits the continuum threshold, your recombination, three atom recombination, becomes resonant because you have just the bound state nearby. And doing to this recombination, of course, atoms are lost, and then this could be observed, including later, this was observed for the first time in the paper by Kramer et al. For three cesium atoms, and was observed also in other systems. No? But essentially, what we have, a continuous scaling invariance, was breaking to a discrete one, we see here. How do we think that? So a very simple way to think about is using the potential 1 over r squared. If the energy is 0, we clearly see that I can change r by some constant. I can multiply by a constant, and the equation, the Schrödinger equation doesn't change. And this, of course, happens when the energy is very small compared to 1 over r squared, for example. This in units, h bar equal mass equal 1. And then when this happens, the continuous scale symmetry is broken to a discrete one. When this happens, you need to introduce a new scale. And as together with that, we also have log periodicity. And this factor here that comes with the strength with this of the 1 over r squared potential is essentially what gives you the geometric ratio between the bound states. And this essentially is the fall to the center that you found in Landau book of quantum mechanics. And this fall to the center was the Thomas collapse that was known since 1935, and also is the source of the Efimov effect. So now we need, in this case, in 3 dimensions, one more scale to fix. The scattering length is not enough. So now, how this was seen, I just flashed this slide. I mean, these equations to solve the trimer problem was long ago proposed by Skoniakov and Termatyriosan in 1956. And this integral equation, essentially, if you take E2 equals 0, E equals 0, or you go to very large momentum, or to the center, or to very small distances, it has scale invariance. So that you can transform in this way the momentum, and so you have still the same solution. And therefore, you should have an homogeneous form. What happens is this integral equation, the kernel is strong enough to allow that this exponent has an imaginary part. When it has an imaginary part, this was indeed discovered by Danilov, then you go to the log periodic solutions of Efimov, and this is the famous Efimov fact. Indeed, the infinite number of geometrically separated states was found by Milos and Feider, but they thought at that time about the Thomas collapse. So Efimov in 70 noticed that, okay, instead of R0 to 0, we make the scattering line to infinity. And then we have these infinitely many bound states. But the idea is that what matters is the ratio between the modulus of the scattering line and the range. This should go to infinity. If the range goes to 0, Thomas collapse. If the scattering length is very large, Efimov effect. Okay, so this is just the trajectory of the Efimov states. So this was discussed long ago by our colleagues, Adhikari and Tomio. Then when you move the dimer energy or the positive scattering line, the Efimov state just goes to the second energy sheet and becomes a three-body virtual state. So if you increase the dimer energy or decrease the modulus of the scattering length. And here is the same. It goes to a continuum resonance when the scattering length is negative. Okay, this is just to show you, I mean, this is the original data from Kramer on the recombination length, and we see that the position of the recombination resonance, three-body recombination, moves to smaller scattering lengths with smaller modulus, and this when you increase the temperature. So this is exactly this movement here. So when you increase the temperature, it's like you increase the energy. So your resonance is going deep and deep, no? And this is exactly the kind of the way it changes. Okay. Okay, so now this geometric, I mean, these Efimov states, I mean, because you have essentially two scales, the dimer energy or the scattering length, no? Dimer bound or virtual energy, and or the scattering length, and one trimer energy, you need one scale. So what happens if you write down the energy of one excited state in terms of the other one, writing down in dimensionless quantity, like the trimer energy, excited trimer energy minus the dimer energy, divided by the trimer energy or the state that is immediately below it. So you have a function, so we say a scaling function, but indeed is a limit cycle. So you can do this state as a function of this state as a function of this state, and so on. You have only one line. And here in red is just the data for the helium trimer, ground and excited state. And these are several other calculations. So this is model independence. that is governing that, because essentially matters two scales. Okay, when we go to mass imbalanced systems, so that factor, this is the square root of the ratios of the two successive trimer energies. So here is the 515. So when you go to heavy light system, it decreases, and this is much more easy. No, the geometric ratio decreases, and therefore is much more easy to observe continuous, I mean, the different resonances as you move, recombination resonances as you move the scattering length. So people have indeed observed this in heavy light systems. Okay, so this is just to give you an idea. So this is a plot that gives you the thresholds for the existence of an excited trimer on the top of a given trimer in the limit of a zero-range interaction. And this is the case for three identical bosons. So in this axis, you have the binding energy of the system alpha beta, and here is the trimer energy. One trimer energy, I say 0, so is the state is one state. I'm looking to the next state, and this is the alpha alpha. So we are in the alpha alpha beta system. So this is where people have measured the trimer of helium-4, but we see that other trimers, like the helium-4 2 lithium-7 molecule may have, because it's inside this boundary here, can have an excited Efimorph state. And this is the Efimorph point. No? So how this curve is universal. Of course, when you put a range, it will move a little bit. No? When you, for example, if you put the effective range. And here is just one study that we did recently with Lucas Madeira. And what happens to these universal functions when we introduce the range of the interaction. So this is the way we parameterize the two-body amplitude. So we just expand in lower order. So this is the effective range. And then we compute the zero-range equation with these corrections. And what we found, so this is a function that we can write essentially in terms of these two dimensionless quantities, that is the scattering length times the square root of the energy, and the effective range times the square root of the energy. So you can do for any state. In this quantum Monte Carlo calculation, we look at the ground state. But look, using the zero-range equations, or the generalization of it, having the range correction, we can have the limit cycle. So these are the dotted lines. And then with the quantum Monte Carlo calculation, we use the Gaussian two-body force and three-body forces, and then we see that is really universal. So these are different range, and essentially we have, I mean, the reproduction, even with the ground state that is quite large. We selected the large ground state in comparison with the range of the interaction. We really see, I mean, even working with the ground state, the limit cycle. Okay, so now what happens when we go to 2D? So in 2D, the scattering amplitude, this was long ago discussed by Adhikari and collaborators. We have the cot delta has some scattering length. This is a dimensionless quantity. And then you have the expansion with log of E and many terms. We can parameterize this as something similar let us say, to give an idea of the range by this A bar. We introduced this in this old paper. That is just the combination of the dimer energy and this quantity A2. So now when we go, of course, we have many terms. When we go to the zero range limit, so this guy disappears, and also all the other terms. We just remain this term here, no? So only one scale remains. And what happens into the Efimov effect disappear. So this was discussed quite long ago by Bruch, and Tijon. So there is no Efimov effect. So the only scale that remains in the zero range limit is the dimer energy. And the trimer, S-wave trimer, has only two bound states that are with energy proportional to A2. And this, I mean, if you change now, if you put the range, so this is the Chon limit, so this is the ground state. If you change this A bar, that gives you an idea of the range, of course, is a dimensionless quantity. And then you see that you have, I mean, a very universal line that we, at that point, we looked at with separable potentials, with different powers, and this is really universal. Now, you say, but what happens if we start to make mass imbalanced systems? When we go to two heavy and one light, we start to have many bound states, but never the Efimov effect, never. So this we discussed with Bellotti and Marcelo, I mean, and quite long ago. And this is essentially the region where we have three identical particles, that we have only two body states. That was the ones discovered by Bruch and Tijon. Okay, so now what we do? Now you want to squeeze. But before doing that, let us remind what we have. In 3 dimensions, 3 particles, we have the Thomas and the Efimov effect that are essentially the same effect. No? And what we need of information? One typical 3-body scale plus 2-body low energy quantities, the scattering length, the effective range. When we go to 2 dimensions, there is no Thomas Efimov effect, no collapse, and there is just the scaling, the dominance of the, for example, of the scaling of the quantities with the 2-body energies, with corrections, but still universal. Okay, so we have now 3 and 2. And what about in the middle? Okay, so in principle, we could think, okay, we can squeeze the system, thinking about we have the atoms in a trap, and then we make an asymmetric trap, and then squeeze in one direction. Okay. So there are other ways of going, I mean, let us say mathematical tools that I will go back to this harmonic oscillator idea. So there is the idea of no integer dimension. Then you can manipulate from 3 to 2. This was indeed discussed in this paper by Nielsen and collaborator quite a time ago. You can compactify one dimension. Then you can go to 3, to 2, even to 1. No? And we can, of course, play with no integer dimensions and look to situations of, I mean, different mass imbalanced systems and so on. Okay? So essentially, these no-integer dimensions, when we look to the momentum space equations, this is essentially like dimensional regularization, what we do. And other people have also explored these ideas. Okay, so first, dimensional reduction by compactification. So here there is, I mean, a rough diagram with X, Y, and Z. And what means compactification? I take the Z-axis and bend and make a circle. If the radius of the circle is infinite, we have, just the line, just the Z-axis. But if the radius is finite, and if I introduce periodic boundary conditions, I can start to squeeze. Why? Because if the radius is pretty small, I will go to 2 dimensions. And the compactification will make the kinetic energy be so high that only it will survive the lowest mode, that is n equals 0. The other modes will be burned because the kinetic energy will go to infinity. So this is one way to reduce. Of course, you have to say, but how I relate this compactification radius with something more concrete? Okay, we are going to discuss that. But first, we just play the game of compactifying. So this is just the two-body amplitude, the inverse of the two-body scattering amplitude with one dimension compactifying. And you can see here, if RZ goes to 0, so this is just disappear, because if n is finite, this will simply drop this term. So when RZ goes to 0, only the mode n equals 0 survives. And indeed, you can compute this analytically. And this expression is just the two-body scattering amplitude. And when you go from RZ 0 or close to 0 to 3, we recover exactly the two-body S-wave scattering amplitudes. Remember the log, and here is just the standard one. This is for negative energies, no? So I'm not introducing the IK that you should have. This is for negative energies. So we are able, with this simple formula, to go from 2 to 3 or 3 to 2. Okay, so now how do we relate this to the harmonic oscillator? What we did was that, okay, we can compute how the two-body energy, binding energy, change with the radius. I mean, it's again a simple, this is analytic form. And we can put, a very short range potential in an harmonic trap, and then see how the dimer energy moves. So when we make this kind of mapping, we see that we can map essentially this formula to a result that comes, or we can parameterize the dimer energy in a trap in one of the dimensions with a short range potential. In this way, we can relate the compactification radius to the oscillator length. So you can compare this, essentially, these two formulas. And what we did, no? So this is in this paper by John Sandoval, was a student of Marcelo Yamashita, no? And then what we did, this is 3D, and this is just the harmonic oscillator length that, of course, correspond to some compactification radius. And then in 3 dimensions, we can have many states. No, these are the Efimov states. You see, this is log scale. They are geometrically separated. So when we move, and this is the scattering length in 3 dimensions. So here, in this direction, the scattering length is very large compared to the harmonic oscillator length. Okay, so we are in the limit of Efimov limit here. You see the geometric ratios. So this is for a kind of system that will correspond to 2 cesiums and 1 lithium. And then you see when we squeeze the system, the FMOV states, they go to the threshold and they disappear in the threshold. In this case, we have a bound dimer. And then goes to you see here in this side, we have 3 states. So these states are the ones that you found for this mass ratio in 2 dimensions. So this is the way the FMOV states disappear. This is one way to see. And we expect that when you squeeze the trap, you eventually are going, if you are able to measure the trimer energy, for example, by resonant association, you should see this kind of effect. And now the other trick was to use a non-integer dimension, no? And this the relation between the non-integer dimension and harmonic trap was discussed, I mean, quite recently by Garrido and Jensen, where they look at the relation of the oscillator length divided by the three-body root mean square radius in 2D. So they found a simple formula playing just with harmonic oscillator potentials for the 3-body. And they checked this formula with Gaussian potential, Morse potential, and they indeed see that this simple formula are able to really give, I mean, the relation between the dimension and this ratio. So these are computed trimers with Gaussian potential, Morse potential, and they really nicely follow that. So at least there is an indication that we can translate the non-integer dimension to the harmonic oscillator length in one of the directions that we are squeezing. Okay, so now we computed, I mean, we went beyond 3 identical trimers. So this was the work by Derek in his PhD with Marcelo. And then when we have a system, AAB system, and this is just the mass ratio between the B and A, no? So this here, in this side, you have, these are 3 identical, that was indeed found by Nielsen and collaborators. What is the region of dimension that you can have Efimov effect? Then you see the boundaries. You can squeeze up to about 2.3. That still you have Efimov effect. You can go above even with dimension 3.8. And this is just the mass ratio between the B and A. So this is the heavy light, and this is light heavy. And then, of course, you see that you can go even to smaller dimensions when you have a heavy light system. So it's more resilient because the distance between the Efimov states are smaller, and let us say the strength of the 1R square potential is larger for heavy light systems. And this is a perspective of this is just the square root of 2 consecutive Efimov states. Then you can see here when you move in dimension. And of course, when you are close to this boundary, the distance between the Efimov states or the two consecutive states start to increase up to infinity. And this is what we see in this plot. So we have here several systems, three identical particles, that, and then you see that the ratio between the state and the excited one increased to infinity. So essentially the excited state should disappear. Yeah. Okay. And indeed, more recently, Derek was able to derive even the wave function, including the energy of the trimer. So this is just a sketch. We are able to get even with, we use Betty Pile's boundary condition. This was a work with Gaston and Marcelo. And with Betty Pile's boundary condition in D dimensions, we are able even to have the analytic wave function. So this is the FADF component. So you have three of that. And we can even use to analyze not only atomic system, but maybe nuclear systems. And this is in the, what we say in the unitarity limit, or when the scattering length goes to infinity. And then you see here the log periodic oscillations. So this is one example for the cesium. Yes, is this lithium, cesium, rubidium system. It's just one example. And then we see the log periodic oscillations. But when you go to the radius to zero, of course, the energy, so this means long distance, the binding energy matters, and then this stops the oscillation. This kappa naught is just kappa naught square. We define it at 2 times the energy. And then, of course, this is just the two distance. We have ρ and r. So we could play even with this wave function. But the continuum we have not done. Okay, so what happens now if we increase the number of particles? So first, I will go to 3 dimensions, 4 bosons. What we discovered quite some time ago together with Marcelo, Lauro, and our colleague Antonio Delfino, quite time ago, that in principle we could have another scale when we go to the 4 boson system. So these are just the Fadeev-Yakubovsky equations. I'm just to emphasize that we can regulate these equations in the limit of zero range interaction, giving the freedom to have another scale. Of course, if you have 2 and 3 body potentials, you are constrained by the scale. But this mathematical construction allows you to move. So this indeed could be interpreted as a 4-body force. And then what we found, as we move the 4-body scale, I mean the short range 4-body scale, to smaller and smaller distance, this is in the unitarity limit, when the scattering length is infinite, states comes from the trimer threshold. So exactly like we saw with Efimov, but this is another cycle. And indeed, when we computed that, so this is the cycle, these are other potentials. You see there are even calculations that follows this cycle. So this is the ratio, these are dimensionless ratios between the trimer energy and the tetramer energy. And this is the excited state, tetramer with respect to the trimer. So these are dimensionless quantity. And we see that we have another geometric ratio. So in principle, we should have interwoven cycles. No? Of course, this interwoven means that we need a 4-body scale. And indeed, in effective field theory recently, it was found that at next to leading order is possible to move the tetramer state.
Tobias,
Okay, so yes.
3 more minutes. You have-
Okay, I'm almost at the end. Great. So now we do the Bohr-Oppenheimer approximation. We can go to many particles. So we just allow light-heavy interaction or heavy light. So with the Bohr-Oppenheimer approximation, the effective interaction between the two heavy, sorry, is my, okay. The two heavy, I mean, have a long-range potential that depends now, the strength, on the number of particles. Therefore, the geometric ratio between the states will be different than the Efimov ratio. And then as long as you have this 1/r² potential, new limit cycles will appear. We have looked at this as a function of the dimension, no, recently. And of course, you can tune. What happens is that now the Efimov, or the generalization of the Efimov factor, will depend on dimension. So in principle, you can turn off cycles when you change dimension. Now, how to move? Three-body scale, or maybe four-body scale. So that is the van der Waals universality that says, okay, for the position of the recombination resonance in atomic traps, so this is the scattering length when the primer energy goes to zero, is about 9 times the van der Waals length. This is in the region of negative scattering length. And this has been understood by, and is revised in this nice paper by Naidoo and Endo, that just when you have the van der Waals force, when you go to the van der Waals radius, the potential just explodes and cut the wave function. So this gives you a scale. And what happens? People indeed found that this is broken. And there is a recent paper by Chapurin and Cornell and collaborators that indeed, even for potassium, found this strong deviation. And of course, when we are close to a, when you have two channels and the closed channel is strongly coupled to the open channel, we can have, for example, three-body forces. And those three-body forces can move. So, okay, so my summary. So I discussed, I mean, scale invariance breaking, Efimov and Thomas effects, the dimensional reduction, and the suppression, of course, of the Thomas Efimov effect. Then I went to more bosons. So for bosons, there is a new cycle. Then scale invariance breaking in any boson system. Bohr-Oppenheimer approximation indicates that maybe there are new cycles, and dimension or schism can turn off independently the cycles. Now the point is how this many-body force we can play or control. This, I think, is not yet well understood. So thank you for your attention.
So thank
Hello?
you. Yes,
Okay.
are you listening?
Yes, yes.
Yes, okay. So thank you very much for the talk. I think we have some time for questions. Yes.
Thank you for the talk. About hollow states, you commented the hollow states in 3D systems, but nothing in 2D. Can you comment about the possibility of observing hollow states also in 2D?
Yes, I mean, this essentially Maybe I move it too fast, but yes, it's possible to have. I mean, when we have, for example, here I discussed mass asymmetric systems, no? That you can have many states, but in principle, you could have, I mean, halo, one heavy and two lights, no? I mean, in principle, you could have, if you are able to tune your interaction. And indeed, I mean, when you go to this limit of zero range interaction, the halo properties will be completely determined by the dimer energy. Suppose you have, I mean, your dimer, your heavy light dimer energy given, so your halo will be determined by that. No? Here I give the example of two heavy and one light, but in this plot you can have many things. So in principle, the answer to your question, yes.
Hi, here's Axel speaking.
Yes, hi Axel.
So I was wondering, you analyzed the dimensional crossover via potential energy, right? In principle, the field of quantum gases also allows to think about a dimensional crossover from 3D to 2D via kinetic energy, in the sense that you have a stack of pancake gases. So with tuning, then the hopping between the longitudinal direction. So if there's no hopping, you are in 2D, but if you allow for a hopping from pancake to pancake to pancake, then you enter the 3D regime. And I'm just wondering whether the way how to practically realize the dimensional crossover may have implications for the Efimov physics.
Yes, I mean, if you go, for example, you are thinking about many pancakes and you have your bosons just moving on the pancakes. Is that what you are thinking?
Yes.
Yes, I mean, this will be a situation of 2D. Now, to go to the situation of 3D, you need to enlarge the pancake, no? Then you should allow the bosons to move. And this is an interesting thing because you could have, I mean, one boson in 2D and the other boson in 3D. So people have discussed, for example, this kind of mixed dimensions even. So in principle, yes. I mean, the Efimov effect, when you squeeze, will disappear. But now, if you squeeze differently the particles, of course, in the 2D limit, it will disappear. But how it will disappear and when, I think is an open question.
Okay, any other question? Yes, Vanderlei.
Oi, Vanderlei. Alô?
Hello, Tobias.
Hi.
Well, my question is more like a comment, but I want to see your point of view. This type of physics is not new, right? We all know the original papers.
Yes.
And so on. And I think it's a very important topic because, you know, we learned from the beginning how atoms can get together, and here comes special features associated with this few body physics. And people like you and many others are being investigating this topic for a long time. What I want to know from you is the better understanding of the topic made us to understanding other things better, right? And so I want to know from you what the evolution of understanding the few body physics improve our understanding of other phenomena in general.
Yeah, I think, I mean, there is first, I think now, one important point that is starting to raise is this problem of the induced three-body forces. I mean, this is yet is not controlled, no? This is by this, we can see by this violation of the Van der Waals University. No, so if you know how to control the three-body force, this is one button more. For example, in the when we look to atomic condensates, this is one example, and of course, how your I mean, this three-body, for example, interaction changes when you move your trap. How I say, aspect ratio, aspect ratio, I mean, is also not understood. I think these are the directions that we could move. And the other interesting direction is how those cycles that are interwoven, how they can appear. Because when one trimer passes the continuum, we have this huge recombination resonance. When a tetramer passes to the continuum, also. But when you manipulate, I mean, the trap in a way to create situations of asymmetry, I mean, going 2D, you may control better these effects, I mean. And the few-body physics can give you a hint how those forces, I mean, how these forces will change when you change, I mean, your trap, no? I think this is something that could, is a direction to go, as I see, no? At this moment, and understand better these interwoven cycles, no? This is something.
Another possibility to answer Wanderley's challenging question is the following. I heard once a very nice talk from a Japanese colleague, a theorist, at a conference which was organized by Heidelberg University in Bad Honnef. And he had the vision to have not only Cooper pairs being, yes, but somehow that was many, many years back. So somehow I never heard about that anymore. So I don't know. At least theoretically, you can calculate some very nice phase diagrams. And I think that would be a quantum jump to transport this few particle physics of Efimov states into the many-body realm, right?
Yes, I mean, if you are able, for example, if you have quasi-particles that behaves as bosons, for example, or different particles, you can, in principle, see those Efimov physics and generalizations of it to more particles, because if there is this kind of cycles, it will not stop in 3, can be in 4, 5, and so on. And if you create this effective degree of freedom of par or even triples that are bosons and so on, and they interact among them, maybe this you can see also this, I mean, kind of universal physics, no? That doesn't need to be the atom itself, can be the molecules or the effective degree of freedom that you have.
Okay, so I think we are running out of time, so I would like
Thank you.
Tobias once again.
Okay, I will stop sharing now.
So thank you, Tobias.
Okay, thank you.
So we should move to our next speaker that is also going to be online, if I'm not mistaken, Tommaso, right? It's not Tommaso? Yes. So, hi, Tommaso. Can you hear me?
Hi, Patricia. Yes, yes.
Hi.
You can see me, right? I see myself in the big screen.
Yes, yes, you are in the big screen.
Okay, so should I share the screen?
Yeah, you can.
Okay, I think I guess you can see it, right?
Yes, it's perfect.
Okay, and just 1 second to adjust
Okay.
my
since
settings here.
Is ready. I think we can move to our next speaker, that is Tommaso Macri. And Tommaso, he's a professor at the Universidade Federal do Rio Grande do Norte, so here in Brazil, in Natal. But this last year, he has been in the US. I'm not sure what he's doing there. Maybe he will tell us, I don't know. But okay, so that's why he's online. So thank you, Tommaso, and I give you the speak. You can start whenever you want.
Okay, so first of all, thank you so much for the introduction, Patricia. It's a great pleasure to have the opportunity to share some ideas with all of you. Of course, I would have wanted to come to be there with you guys a lot, but unfortunately, I was not able to travel at this time. I heard from the previous talk the voice of Axel. So hi, Axel. I hope that we can meet in person soon, as well as Vanderlei. I also want to acknowledge for the invitation, Arnaldo. I don't know if he's in the audience right now. But again, it's been would be really great to see ourselves in person very soon. So today, I promise that I will not take too much time. I see that I know that the conference is finishing, the workshop is finishing soon. But still, I want to talk a little bit about these ideas related to the so-called quantum boomerang effect in localized systems. And to do that, first of all, I would like to acknowledge some of my closest collaborators that helped me to get a better understanding of this effect throughout the last couple of years. So I would like to start from thanking Flavio and Arsenio, who are postdocs at the Federal University of Rio Grande do Norte. Santiago, who is a second-year PhD student, who is actually there in the audience with you. He is currently working on the so-called classical analog of this boomerang effect. And of course, if you guys have any questions regarding this topic, please just ask Santiago. I guess he would be very happy to explain his recent findings. And also, I would like to acknowledge very fruitful discussions and collaborations with Patrizia Vignolo from Nice, as well as David Weld from UCSB, from the University of California, Santa Barbara, with whom we actually collaborated to demonstrate experimentally the quantum boomerang effect in the so-called quantum kicked rotor model that I will discuss briefly at the end of this presentation. So the talk today will be focused mostly on these first three works that have been published last year. And again, if you have questions regarding the classical version, please refer to Santiago. Okay. So I would like to start basically providing some context for this boomerang effect by basically reviewing the physics of the prototypical Anderson model in one dimension, which is a single particle hopping model with constant hopping J and on-site energies epsilon I, which vary randomly within an interval of width W from minus W over 2 to W over 2. So an important result in the context of Anderson localization in one dimension is that all the eigenstates are essentially localized. There have been several experimental realizations of Anderson localizations in a wide spectrum of physical systems, Probably the one that that we are mostly aware of are those within the field of cold atoms, but also other physical systems like lighting fibers or lighting biological media display similar effects. What we see here in the figures on the right is essentially the so-called experimental verification of this localization property when we release an initially prepared wave packet within an harmonic trap after a certain amount of time t. What we observe is that the width of the system essentially saturates to a constant value in the presence of an external random potential, whereas it grows linearly in time, as we know from elementary quantum mechanics, in the absence of an external random potential. Another important result is that, as you can see, the tails of the distribution are essentially exponentially localized. So again, I want to highlight that this is characteristic of the 1D. In higher dimensions, the physics is slightly different. I will mention some results later on. So the boomerang, to understand the boomerang effect, the physics essentially is very similar. We can take the same Anderson model that we have seen in the previous slide, but now we want to understand what is the dynamics in the presence of an initial momentum kick. So again, we have a random potential, basically trivially schematized by this continuous black line here. We prepare an initial Gaussian wave packet, but now we imprint a phase given by this with this momentum k0 that basically kicks the wave packet in one direction, for example, along the positive x-axis. And we wonder what is the dynamics after sufficient long times of this initially kicked wave packet. So this question, although it looks like very elementary from the physical perspective, it was nicely described in this PRA paper by Dominique Delalande and Nicolas Chehoret a few years ago. And basically, mathematically, the problem is, again, very simple to be described. So if we take, we want to compute the average position as a function of time. So we need to compute this integral of x multiplied by the density as a function of at time t. And we start with a Gaussian initial wave packet for simplicity. So here we have a normalization constant, m Gaussian, times a phase factor e2i k0 x. Now, if we blindly start to analyze this problem from a purely classical perspective, so let's take, for example, a Brownian particle within a medium. What we would obtain is that if the particle is static at the very beginning, we would observe that the particle would start again realizing a Brownian motion, and it will spread over time symmetrically around the initial position at x equal to 0. If we instead we kick the particle in one direction, let's say to the positive direction of the x-axis, what we would observe in this classical Brownian analog is that it will initially move ballistically, and then it will saturate to a constant value. So essentially, the particle will move initially ballistically, and then it will end up at a finite position x equal to L, where L is of the order of the mean-free path of the system. Now, it turns out that in the quantum analog, so in the presence, when we study the Anderson model in one dimension, the physics is actually quite different from this classical analog. And in particular, let me also highlight that this specifically the physics of this classical analog is what we are actually currently investigating to make a more clear parallelism between this quantum boomerang effect and what happens in classical subdiffusive systems. So again, if you have questions, we can discuss about that at the end of the presentation. But now we want to focus purely on the quantum regime. So here, what we see Let's focus first on these figures on the right. We plotted the center of mass position as a function of time t. And what we observe is that initially, we take, again, another important thing is that we take an average over several realizations. We see that initially the particle spreads moves ballistically, and then it makes a U-turn, and for large times it returns to the origin, which is sort of quite counterintuitive, right? Especially if we compare this behavior with the classical one. The picture on the right, on the left, instead displays the probability density. We see again this sort of light cone behavior that, of course, spreads symmetrically with respect to the position x equal to 0, which is the origin. So initially, we have again this wave packet, which is very much localized around x equal to 0. But now we plot this density as a function of time. And we observe that, of course, initially, as the particle spreads ballistically, like in the picture on the right, we see that there is an enhanced probability density that moves along the positive x-axis. But then, if we compute the average, which is given by this dashed line, we see that there is a concentration of probability density around the origin, which is also consistent with the picture of localization, in the sense that eventually the system is always localized, so the particle will always end up into basically being localized within a region of the order of the localization length of the system. But the counterintuitive fact in this respect is the fact that the particle indeed goes back. So it first moves ballistically, but then it goes back to the origin. Now, this is basically the main result for the case of a one-dimensional system. What happens if we extend the same study to the three-dimensional case? Well, in 3D, we know that the physics of the Anderson model is slightly different. There is a metal insulator transition as a function of the strength of the disorder W. In particular, for the small disorder, the system is delocalized, whereas for large disorder, in particular, above a certain threshold of the disorder, that for the 3D Anderson model takes the value of 16.5, the system instead, all the eigenstates will be instead localized. So if we take a sufficiently small disorder, then what we will have is that there will be enough eigenstates which are delocalized and overlap with the initial state psi x naught, so with our initial Gaussian wave packet. And what we observe is that if we plot the average value, so the center of mass position as a function of time, it will essentially converge to a constant value, which is sort of consistent with that diffusive picture that we have seen at the very beginning. However, if we instead cross this threshold value of the disorder and look at the same center of mass position for large times and large disorder, we see that instead the center of mass goes back to the origin. So we observe again this physics of the quantum boomerang effect. Now, the other important observation relative to this three-dimensional case is that the boomerang effect itself can be used as a sort of probe for detecting the position of the metal insulator transition. Indeed, by doing a rescaling of the position of the center of mass by time with a certain power t to 1/3, which is essentially what it is observed in the case of the critical point, we observe that there is a nice crossing of these curves at precisely the value 16.5, which is consistent with the other results in the context of the 3D Anderson model. Now, the question that we tried to answer was to provide an interpretation, or sort of a deeper interpretation, to these numerical results that were presented in this paper in 2019. Now, it turns out that the physics of the quantum boomerang effect is actually very much related to both, of course, localization, but also to the intrinsic symmetries of the class of disordered Hamiltonians that we are considering, as well as the symmetries of the initial state, which we take in this particular case as a Gaussian wave packet. But as you can see, we could take an initial arbitrary wave packet with different properties than the one that we are looking at the moment. So let me walk through the discussion of how symmetries actually become relevant in the sort of proof of this quantum boomerang effect. We will focus in particular for this example in 1D, but I will show in a minute an example in 2 dimensions just to contextualize that this framework works in a more general setup. Now, let's consider reflection, which maps position x into minus x, and time reversal symmetry, which maps t to minus t. Here we consider a class of disordered Hamiltonians which are invariant under RT. So in particular, the action of the reflection time reversal symmetry onto this class maps this class of Hamiltonians into the same class. We take, for example, a single realization of the Anderson model in 1D. This is, of course, not invariant under RT. It is invariant under time reversal because the coefficients are real, but it is clearly not invariant under reflection symmetry. In particular, the on-site energy at site J is not equal to the on-site energy, not necessarily equal to the on-site energy at site minus J. However, given a certain realization of the Anderson model in 1D, we can map, by applying RT, so by applying reflection and time reversal symmetry, we map it into a different realization which still belongs to the same class of Hamiltonians that belong to the 1D Anderson model. So if we take as a whole the set of disordered Hamiltonians that are described by the Anderson model, they are instead, yes, they are indeed invariant under RT, but singular realizations not necessarily display the same type of symmetry. So this is one fact. So this is what we get if we focus on reflection time reversal symmetry on the Hamiltonians. What happens instead if we focus on, if we apply the same reflection time symmetry into onto the initial state? Well, we observe that if we apply RT into psi x naught, what we get is that clearly time reversal symmetry will take A, so the constant, the prefactor, trivially to the complex conjugate. It will leave unaffected the Gaussian term, but instead we'll map the phase e to I k naught x into e to minus k naught x. Now, if we apply R on top of this time reversal symmetry initial state, time reversal symmetric initial state, what we get is that A will still be a complex conjugate of A. The Gaussian will remain unaffected, but now the e to minus I k naught x will go back to I e k naught x. So if we neglect trivially, or if we take a constant prefactor, a real prefactor A, or normalization prefactor A, we observe that this particular initial state is an eigenstate of a reflection time symmetry. So far, so good. Of course, if you have questions, just either interrupt me or we can clarify all these points at the very end. Now, if we assume that our initial, the class of Hamiltonians are invariant under RT, and the initial state is an eigenstate of reflection time symmetry, what we are interested into computing, again, is the center of mass position as a function of time. So now we need to focus on the density of the system at times t. This can be actually expanded in terms of the eigenstates of the Hamiltonian, which are here represented by phi n and phi m. There are these phase factors here, which are the dynamical phases that appear when you perform time evolution. And these epsilon n and epsilon m are the eigenvalues of the system. Now, since the eigenstates are localized, the system is in general constrained to a volume given by the localization length, which is proportional to the mean free path of the system. This also defines a typical level spacing delta, which is the inverse of the density of states times the localization length, with a corresponding localization time, which is proportional to h bar divided by the this level spacing. Now, beyond that characteristic localization time, essentially all the oscillatory terms vanish, and we end up into an expression psi x, or average value over realizations at sufficiently large times, so not necessarily infinity, but times which are much larger than the localization times, which is given by essentially what we would call the diagonal ensemble. So we take just the diagonal terms of this expansion of the density in terms of the eigenstates of the Hamiltonian. Now, another important fact is that this expression is actually independent of the sign of time. So we would get essentially the same expression whether we are propagating forward in time or backward in time, right? Now, if we compute the average value, the expectation value of the position operator into the class of Hamiltonians given by H, or actually to be more precise, into for a specific realization of this class of Hamiltonians H, what we will get if we now apply RT and RT minus 1 to this to the expression for the expectation value, we would get that basically, since the initial state is taken to be an eigenstate of the Hamiltonian, of the RT, and in particular, if we take A to be a real, the prefactor to be a real constant, we get either plus or minus, and this plus or minus can be generically appear whether we take either Gaussians or which are of course symmetric with respect to the origin, or anti-symmetric. In that case, we would multiply this Gaussian type by a node power of the position of the position x. In that case, we would get either plus or minus. The same thing takes place for the cat psi naught, but the magic takes place in the middle of part of this expression, where we have these the propagators. So e2 I h dagger t, and e2 minus I h t. So if we have an emission Hamiltonian, h dagger is equal to h, so there is no problem. But this effect actually also generalized to the case of non-emission Hamiltonians. I will not spend time on that, but if you have questions, we can discuss about that later. So again, if we now map, if you apply RT to this exponential here, we will map a single realization H into a new realization of our disordered class of Hamiltonians that we will call H tilde, okay, which is given by the application of RT into the Hamiltonian H. And then if we apply RT on the operator X, what we will get is that time, of course, that does not, time reversal symmetry will not affect X, but reflection symmetry maps X into minus X. So we'll gain a minus sign in front of this expression here. So by applying this consecutively these RT operators into this expression, we get that the expectation value of the position at time t for a single realization of the Hamiltonian, of the disordered Hamiltonian H, is equal to minus the expectation value at times minus t, where of course t the t is mapped into minus t by applying the time reversal operator capital T, for computed for a new realization of the disordered system given by H tilde. And now what we do is we average over all the disordered realizations, and therefore if we average over all the disordered realizations, what we get is that this average at time x at time t equal to plus infinity is equal to minus the expectation, the average of the expectation value taken at times equal to minus infinity. On the other hand, the fact that the probability density instead is invariant under time reversal, so from t to minus t, we end up into, so the only way in which this expression here is compatible with this expression here is that for sufficiently large times, the average of the expectation value of the position is equal to 0, which is precisely the proof of the fact that we have the so-called quantum boomerang effect. Now, I mentioned at the beginning that, so I apologize for taking so much time to basically highlight the sort of analytical motivation for this boomerang effect. I want to now focus on some numerical results that essentially highlight how this symmetry-based proof of the boomerang effect is actually relatively powerful. I want to focus into a so-called to the so-called Harper-Anderson model, which is essentially the same Anderson model that we have seen before in 2 dimensions. We consider the case of sufficient strong disorder, and on top of that, we add some fluxes that penetrate the plaquettes of this 2-dimensional square lattice Anderson model. So in this case, of course, we expect that the time reversal symmetry is, of course, broken by the presence of time reversal. But on the other hand, what we are actually interested in, as a matter of fact, is the invariance of this class of disordered Hamiltonian under the simultaneous applications of not only time reversal, but also reflection symmetry. And if you consider the symmetries of these phases that you need to attach to the Anderson model to the Harper-Anderson model to be effectively representing a model that displays a magnetic field, so in the presence of a magnetic field, you end up demonstrating essentially that the class of disordered Hamiltonians represented by the Harper-Anderson model is indeed invariant under the simultaneous application of reflection and time symmetry. Now, what is not invariant under the simultaneous application of RNT is the initial state. In particular, the initial state the initial state is invariant under RNT along the direction x. So if you take again reflection with respect to x, you see that the same argument that I was discussing before applies. So this is indeed an eigenstate. But if you instead apply reflection time symmetry, where the reflection is taken along the y-axis, this is of course not an eigenstate. And it is not an eigenstate because when you apply R, you get basically this Ry, this phase factor remains unchanged. Whereas if you apply T, you get a minus I k naught x. So trivially, this phase fact, this initial state is not invariant under the simultaneous application of Ry and T. So what is the outcome of this is that basically this argument that we developed here on the left part of the slide does not necessarily hold for the case of the Harper-Anderson model along one of the 2 directions, and specifically along the y direction. So this can be clearly seen when we monitor the dynamics of this wave packet, which is initially localized around the origin. And what we see is that initially the wave packet will try to perform a sort of cyclotron orbit because we have a magnetic field that penetrates that crosses the 2-dimensional square lattice. But after a certain point, basically the disorders start to play a role. And what we see is that the system performs the analog of a U-turn, but now in 2 dimensions. It goes back. You see that it goes back to for sufficient large times. It essentially wants to reach the initial value of the x-axis, which is basically x equal to 0. But on the other hand, along the y-axis, it does not go to 0. And this is again a reflection of the fact that this argument for the boomerang does not hold along the y direction. This can be done a little bit more explicitly if we separate the dynamics along the 2 different directions. And what we see is that along the x-axis, indeed, we see that this nice U-turn. and the system wants to go back to the origin for sufficiently long times. Along the y direction, instead, where this reflection time symmetry is instead broken, we see that, again, ballistic motion for small times, but then the system, the y coordinate saturates to essentially a constant for sufficiently large times. So in 2 dimensions here for strong disorder, what we observe is that there is a partial breaking of the boomerang effect due to the fact that the initial state is not an eigenstate of the system, of the class, of the simultaneous application of reflection and time symmetries. Now, so far so good. Now I want to slightly change gears and discuss an apparently totally unrelated model with respect to the class of disordered Hamiltonians that I was considering before. And I want to move to the so-called classical, to the quantum kicked rotor model, which has a very famous classical counterpart, which is called the classical kicked rotor model, which is, again, a sort of representation of what a very famous dynamical map in classical dynamical system, which is called the Chirikov map. Now, the classical kicked rotor is essentially represents the dynamics of a particle or a pendulum, if you wish, where the gravity, which were described by this potential with strength k cosine theta, is switched on periodically in time, where the period is labeled by this capital T here. Now, it turns out that classically this model is actually quite rich. If you look at these phase portraits for different values of k, so the strength of this potential energy, what we observe is that for small values of k, the system displays regular orbits. But then if we cross a certain threshold value, the system essentially displays a completely chaotic motion. Now, one might wonder why I am introducing this model. What is the relation of this model with the topic that I was discussing before? Well, the reason is that the kicked rotor in the quantum regime can be mapped into a one-dimensional Anderson model with a diagonal pseudo disorder and an exponentially localized opt-in channels. This observation, of course, is not ours. It's well known in the literature. It dates back to the 80s. There are some works by Casati and Guarnieri, Szpeliansky, and others that essentially prove the mapping of the quantum kicked rotor into an Anderson model in momentum space. We can go very quickly through this derivation, but of course I would like to point out to the original references if you want to have a clear understanding of this mapping. But I would say it's actually quite interesting, so let me just briefly sketch the proof. So if we start from the quantum kicked rotor, where we promote both the momentum and the position to operators, and we study the evolution of the system through this Floquet operator, where this V is essentially is equal to the strength of these kicks, k times cosine theta. If we rewrite this potential energy term of the propagator in terms of an auxiliary operator M, capital M, and introduce the Floquet quasi-energies E alpha, we can rewrite the eigenenergy equation in terms of this operator M. By introducing, again, an auxiliary vector psi alpha, which we expand in terms of the momentum basis given by these M cats, we finally end up into an eigenvalue equation, which resembles very much the eigenvalue equation of a 1D lattice model with local energies epsilon n, which are given by these sort of pseudo-random numbers given by the tangent of these of the Floquet quasi-energies minus n squared. Now, the quantum kicked rotor model is also very well known in the literature, not only for really several theoretical discussions, but also for many experimental realizations. And here I just I just mentioned a few of them, but if you're interested, there are very many other references in the literature, and we can discuss about that. If you're interested, just reach out to me and we can. I'm super interested about this topic. Now, what I would like instead to point out is that the experimental verification of the quantum boomerang effect into this model. So we saw what is the link. So the link is that the quantum kicked rotor can be mapped into an Anderson model in momentum space. So since at the very beginning of this presentation, we highlighted the nice features of the quantum boomerang effect into Anderson-like models, we would expect that if we investigate the dynamics of the quantum kicked rotor in momentum space, so if we monitor the dynamics of a wave packet now in momentum space, we might be able to recover the physics of the boomerang effect. This is indeed what was done, what we did in collaboration with the group of David Weld at UCSB. And what you see here is essentially a sketch of the dynamical protocol that they used in the experiment. So they prepared a Gaussian wave packet, which is initially basically centered around a site of a standing wave, so an optical lattice. And then after a time alpha t, where alpha is, for now, it's an arbitrary number that monitors, that basically enters into the definition of this Floquet and of this Floquet operator, the Floquet dynamical propagator. They start kicking this optical lattice with a phase shifted optical lattice. So you see that there is some phase difference between the initial optical lattice labeled by this blue curve and the dynamical, and the kicked optical lattice, which is switched on and off periodically in time with period capital T. Now, the shift in the between the two optical lattices basically represents a kick, is the equivalent of a kick now in real space, because we are now the important thing that to keep in mind is that the optical lattice, the quantum kicked rotor is mapped into an Anderson model in momentum space. So if we attach a phase with an initial kicking momentum in the real space Anderson model, we need here a kick in real space, which represents basically the analog of the momentum space kick in the real counterpart of the Anderson model. So after that, after a variable number of kicks, they perform a time of flight measurements, which gives us access to the momentum space distribution of the BC, and we monitor the expectation value of this momentum distribution. What we observe is that is a dynamics which is very similar to the dynamics of the real space Anderson model. So here we see a U-turn, and then nicely the wave packet or the center of mass in momentum space saturates to a constant which is compatible essentially with zero. So again, a confirmation of the boomerang effect. There is a tricky point here there are some technicalities. Let me just mention one of them. So the real initial state is invariant under the application of complex conjugation. We just take an initial state which is a real state at the end of the day. But then what we end up by applying the properties of this Floquet quasi-operator, so this Floquet propagator, we end up in having some relationships between the average, the expectation value of the momentum after m kicks with the gauge factor 1 minus alpha, which is related to the average momentum after minus, so if we propagate back in time, minus m, analog to the proof that we were discussing at the very beginning, with phase with gauge factor alpha. So in particular, if we focus on alpha equal 1 alpha, we end up with this relation here, the second line. And then by applying, recalling the localization property, which gives rise to essentially a so-called diagonal ensemble, where the probability density is independent of time for sufficient is independent of the sign of time for sufficiently long times, we end up by proving that the average momentum for sufficient long times for alpha equal 1/2 is equal to 0. This can be, of course, also checked experimentally if we essentially initialize these kicks with a variable number, with a variable time t, and we observe that indeed, only in the case where alpha is 1/2 or very close to 1/2, the momentum saturates to vanishes for sufficiently long after a sufficiently large number of kicks. Instead, if we take alpha, which is far from 1/2, in particular 0.3 or 0.7, we end up into a constant value which is far from 0. In particular, this is minus 0.1 and this is 0.1. A second important observation before concluding is that we observe a breaking of the boomerang when we essentially stochastically kick our condensate, and this is related to the breaking of localization. Indeed, if we monitor the energy, the kinetic energy as a function of the number of kicks in the localized, so for periodic kicks, we observe that the kinetic energy essentially goes to a constant. But instead, if we kick stochastically, the average momentum, the average kinetic energy increases. And the counterpart in the observation or of the boomerang effect is that in the periodically kicked rotor, we observe that the momentum indeed goes to 0. Instead, in the stochastically kicked, the breaking of localization also implies that the long time behavior of the average momentum goes to a constant value, which is non-zero. So to conclude, in this presentation, I wanted to guide you through the physics of the so-called quantum boomerang effect, which can be used as a solid test also for Anderson-localization. I briefly sketched the proof and the fact that symmetries are actually very relevant to the understanding of the microscopic derivation of the quantum boomerang effect. Quantum boomerang effect can be also easily generalizable to many particle systems in the non-interacting limit. The proof is essentially the same. It works for both bosons and fermions. And we were also able to prove using very simple arguments that mean-field interactions in general destroy the boomerang. There was also, this can be found in our PRB letters that we published last year with Flavio. And there is more recently a much more detailed study by Dominique Delande in a PRB paper that appeared earlier this year. And finally, in the second part, I wanted to highlight how the boomerang effect can indeed be experimentally observed in an apparently unrelated model, which is the quantum kicked rotor, which, however, displays Anderson-localization in momentum space. And therefore, the boomerang effect is indeed there if we not only study it theoretically, but also experimentally in the lab. So with this, I would like to conclude and thank you for your attention.
Hello.
I cannot. Yes.
Hello. Yeah. Are you listening, Tommaso?
Yes, I can.
So thank you very much for your presentation. Yeah.
Thank you, Patrice. Any questions? I cannot hear anything.
Hello. Yeah, now it's on.
Okay.
Is there any reason that the same
Vanderlei, is it Vanderlei? I cannot really hear you.
we are having a problem with the microphone here.
Okay.
Okay, I will try to be fast. Is there any reason why?
Vanderlei could just hear, is there any reason why? And then it muted.
Sorry, Tommaso, there is a new microphone that is coming.
Oh, okay, okay.
Oh, new microphone. Is there
Yes.
any reason that I should not expect it, or I should expect the same effect with light?
Great question.
I have a wave packet of light propagating and finding a very nice structure with some randomness on the index of refraction. Would I find the equivalent effect?
So that's a very good question. There are, I think, there are probably different answers depending on the physical realization, I guess, of the model that you have in mind. In general, I would say no. There are no differences. If you can map the dynamics of the wave packet into the same model that we are, or the class of models that I briefly sketched, there should be no difference at all. I can be more specific if you want, Vanderlei, but it might take some time. But we thought a little bit about that. For example, there is one probably very simple analogy to the models that I was considering, which is probably the case of light propagating in hot vapors, where you can map the dynamics in those systems by basically mapping the Maxwell equations into a Schrödinger type of equation by using the so-called parallax approximation. And we haven't proven anything. We haven't thought too deeply about that, but you can see that there are clear analogies, and I would expect essentially the same behavior. And clear, of course, the parallelism goes with the fact that time would be replaced with the propagation direction, for example. But I would say there is a clear analogy in terms of the equations, so I would expect it precisely the same behavior.
Okay, another question.
Hey, Tommaso, thank you for the lecture. I would like to know if quantum boomerang effect, could it be a necessary or a sufficient condition to observation of Anderson localization? How do you can characterize it?
That's a very good question. Can you say your name? Because unfortunately I cannot see.
My name is Sheila.
Sheila, hi. That's a very good question. And indeed, this is something that we actually asked quite a lot over the past year. And that's the reason why we decided to investigate the same, basically this very same question in the case of also classical systems, where you don't clearly have the physics of Anderson localization, but still you can observe a very similar physics in subdiffusive, in the case of subdiffusive dynamics, when you have a particle which is interacting with an external bath. So of course, in the quantum case, you don't have a bath. We don't have a bath. We could have, but we just consider a static random potential. In the classical case, we started from a Brownian particle interacting with an external bath. A prototypical model is the so-called caldera-legged model, for example, which you can take either the classical or the quantum version. And what you observe is that depending on the spectral properties of the bath, you can observe a dynamics which is very similar to the one that we observe here. So you can indeed observe in for some specific type of baths, you can observe the boomerang effect. Now, I wouldn't call it a quantum boomerang effect because you can have it precisely in the pure classical regime. And therefore, going back to your question, we believe that the quantum boomerang effect, the boomerang effect, is not necessarily specific to the localized systems. Probably to be the most fair type of answer that I can give, which probably would sort of complement the talk that I presented today, is that the boomerang effect appears when you have, in general, subdiffusive dynamics. The case of Anderson-localization in 1D is very peculiar because you have absence of diffusion, so it's sort of extreme regime. So if you don't have diffusion, you observe the boomerang. But also in the case where you observe subdiffusion, which means that the exponent of the width of the exponent of the sorry, if you study the evolution of the width of the wave packet as a function of time, typically it will scale like t to the power alpha. When alpha is smaller than 1, you also observe the boomerang effect when you monitor the center of mass position. So again, this boomerang effect, in our view, is much more general than the one that we discussed over the past couple of years in these papers and these results that I displayed today. But this is still a little bit under investigation, so we will soon have a preprint about that. Santiago is, of course, involved, my student, and I look forward to discussing about that much more in the near future. But thanks for the great question.
Okay, next question.
Hello, Tommaso. Nice talk. I want to ask you about the width of these experiments, because you cannot do a pulse exactly like a delta. You must have some width. How this width destroy or enhance? What happens when you make this width bigger in this kicked rotor in the experiments?
A great question. I guess you are Arnaldo, right? Is it?
Yes, yes.
Okay. Hi, Arnaldo. Yes, so that's a very good question. This question has been discussed briefly in by the experimental colleagues, and we observed that it is quite robust to the shape of the kicks. So indeed, you can take also Gaussian shaped kicks instead of really delta localized in time, and you observe a very similar dynamics. So there is a relative robustness of this effect with respect to the shape of the kicks. Yes.
It's interesting to analyze which scale it's not good enough. What's the time scale of this pulse, the width of this pulse compared to which reference that you say, oh, this width is not good. You must be smaller than something. I think it's interesting to analyze. Well,
Right.
Okay.
Yes, I don't know if we. I don't remember. Honestly, I don't remember if we did a systematic study of the boomerang with respect to the shape of the kicks or the duration of the kicks. But I can certainly go back to the original, to our paper and try to have a look.
Yeah, thanks, Tommaso, for the inspiring talk. Let me ask the following. The most surprising feature of this boomerang effect is that there is a certain time scale when the particle returns. And the question would be now, how does this time scale change with the disorder strength or the correlation length of the disorder?
Okay, so first of all, hi Axel, very nice to see you. Well, I don't see you, but I can hear you. That's a very good question. The time scale we believe is very much related to the localization time, the one that we defined as the inverse of the basically inversely proportional to the basically to the spectral gap. And it's a good question. We haven't investigated yet as a function. So the question you're asking, how does that U-turn time scales with the disorder strength, for example, or other parameters of the Hamiltonian? That's a very good question. I think no one has really studied that in detail. Probably my guess is that you can possibly do some analytical calculations in the case of weak disorder. But I know that you are an expert, so perhaps you already have some some ideas on how to do that. But my guess is, my point is that probably you would observe that the typical time scale in which you observe the U-turn is proportional to the localization time. And that localization time depends, is a function of the disorder strength. Then the analytical behavior, honestly, I don't really recall. We haven't done any calculations, but I guess you can guess some values, some dependence. You are very much experienced in that accent.
Thank you.
So Tommaso, I also have a small comment. So at the
Please.
beginning, you said this boomerang effect could be associated with Anderson-localization and could be used to as a solid test for 3D Anderson-localization.
Yeah.
So my point is that on our work in Florence and also in Marco's work, it was pretty much clear the signature when you start localizing your system. The matter was how to calculate the energy in order to match this energy with the mobility edge.
Right.
So I don't know if doing like with the boomerang effect, we gain too much on it, because the localization was pretty much clear when it started. It was a matter of knowing how to extract the energy of the system in order to really match it with the mobility edge energy.
Right. Right. So yeah,
It's nice that there is a connection, but I don't know if it helps that much on extracting the mobility edge itself.
probably extract the mobility edge and not much, extracting the critical value of the disorder. That was possibly the connection that that was identified in the original paper on the boomerang effect. I agree with you. This is in a sense, this is a sort of global effect, if you want, because we are not really looking at the precise shape or precise energy of the eigenstates. This is not really what we have access to, this dynamical effect. What you have access to is a sort of global or integrated quantity, which is the average position, so the center of mass of the wave packet. Now, the point is that the dynamics of the center of mass displays some features which allow to distinguish between these two dynamical regimes, the one in which you are fully localized for sufficiently strong disorder, and the one in which you are instead delocalized or partially delocalized for a weak disorder. The question on the energy thresholds, the mobility edge, is a bit more delicate. Again, it depends specifically on the energy. I agree, totally agree with you. And possibly you don't have access to that through these experiments.
Okay. So any other question? Yes. Last one.
Hi, Tommaso. So my name is Henan. So my question is a bit technical. You showed in one of the slides a relation between the correlation length and the mean free path. And I wonder, what is the definition of this mean free path? Do you define it from the diffusion constant? And is this relation, is this relation valid for all dimensions, or is there a range of validity between the relation of the mean free path and the localization length?
Right. So I think I took this expression from the original paper, but I think that they commented that that expression is actually valid in the case of weak disorder. So that's the regime where it holds. But I can point you to the original paper if you want to have further details.
Thank you.
Okay, so let's thank you, Tommaso, once again.
Thank you so much, everyone. Have a good conclusion of the workshop. Bye-bye.
Ciao. So now people, coffee break time. Everybody's going to be happy.
happy to have the presentation by Lauro Tomio. The talk will be on dynamical vortex production with periodic time-dependent perturbation applied to dipolar and non-dipolar EC mixtures. Okay, we're looking forward to the talk.
Okay, thank you very much for the invitation also to present this talk. So that's the title, the talk. It's a dynamical vortex production with periodic time-dependent perturbation applied to dipolar and non-dipolar back mixtures. I'm from Institute Física Teórica, and after a long time, it is my first time that I'm talking the old Institute Física Teórica in Pamplona, because now we are in UNESP in Barra Funda, as you know. So that's so these are some collaborators in this work that I've done now. Sabari is a new postdoc that we have, and Asa is a student that made a lot of calculations also here, and Kishore now is in New Zealand, and also we have Ashton Bradley in the first part that we have some collaborators. I also have some collaborators here in USP also, but in a different subject where we are talking about bubble geometry that we are doing something here with Arnaldo and his students also. So the aim of this talk is to report some recent computational studies that we have done on the dynamical production of stable vortex and quantum turbulence by considering boson condensates confined in pancake-like traps perturbed by time-dependent periodic interaction. In this regard, we have recently investigated two kinds of back systems. The first is we have considered vortex and turbulence generated by a steering time-dependent interaction in a two species coupled mass imbalanced condensate. For the perturbation, we have considered a slightly modified elliptically periodic potential. The approach is applied to the experimentally accessible binary mixture, rubidium cesium and rubidium, which allow us to verify effects, possible effects that we have of mass difference in the dynamics. This was recently appeared in Physical Review A. Okay. Next, I will report a more recent study we are preparing for publication related to a single species dipolar system under periodic linear and circularly moving Gaussian-like obstacle, which is added to the trap as a perturbation. In this case, we have investigated the critical velocities of the Gaussian obstacle for nucleation of vortex dipole and clusters. So that's the outline of my talk. And first I talk about the steering binary back and some formalism and give the dynamics of steered vortex formation, kinetic energy spectrum, and rotate frame field. And after I show some results and my conclusion on this topic. And because it creates quantum turbulence and also vortex generation at the end. Next, I shift to dipolar system and the periodic moving obstacle. The formalism for dipolar back, again, a Gaussian perturbation, dipole-dipole interaction, and the result. And my conclusion on this topic. Okay, so quantum turbulence, many people here already have talked about, but I'm just repeating something here. The name given by the turbulence flow of a fluid at high flow rates of quantum fluids, such as superfluid. Also, this is already well done, shown also in Wikipedia with a lot of reference on that. So first was suggested by Richard Feynman was the connection of turbulence with superfluid via the quantized vortex line. The dynamics of quantum fluids are governed by quantum mechanics rather than classical physics. Some examples of quantum fluids include superfluid helium-4 or Cooper pairs of helium-3, and boson condensates, polariton condensates. So it is being noted also that quantum fluids exist at temperatures below the critical temperature at which boson condensation can take place. So quantum turbulence is an apparently random tangle vortex line inside a quantum fluid, as indicated by the experiment and numerical simulation. And the two main questions in this study is, are vortex tangles really random, or do they contain some characteristics, properties, or organized structure? And how far one can compare quantum turbulence compared with the classical turbulence? Okay, here we can show some picture about classical and quantum turbulence, the comparison here. Classical turbulence can be seen in classical fluid in many kind of ways that you know, by chaotic motion with airflow. Turbulence in the deep vortex from an airplane, for example, and ocean and atmospheric mixed layer. And quantum turbulence, the other side, is characterized by the tangle of quantum vortex defect in quantum fluid. The quantum turbulence has been studying these systems here and atomic bosons condensation. Here is a picture about Jupiter with a red spot, and here is two large parts of potential here are superfluid. And here are one of the first experiments on that by the group here of Bagnato, but published in 2009 about the density profile in quantum turbulence observed by time of flight expansion and the distribution of quantized vortices inferred from here, where the vortices are depicted by the black region. So here is one example also that we have studied some time ago, is about turbulence occurred due to Rayleigh-Taylor instability that mixed system. In that case, with two systems, coupled system, but with non-miscible situation, immiscibility. Now let's go to that formalism of the first part. Is the first we have to go to the coupled Gross-Pitaev thing. I lost the pointer here. The Gross-Pitaev equation is cast in a dimensionless format with the energy and the length units given respectively by this unit here. And here's the length. We are assuming the first space, the less massive one, as our reference in our unit system, such that this is the frequency that is in our unit. Within this unit, for simplicity, we first adjust the confined trap frequency of both species, such that the dimensionless, non-perturbed three-dimensional traps for both species can be represented by the same expression given in this way. Where this zero is a two-dimensional harmonic trap, this way there is no explicit mass dependence factor in the trap potential, which will remain only in the kinetic energy term. And here is our Gross-Pitaev equation. Here is the mass relation here, that it's two-dimensional moment operator, and G are the two-body contact interaction related to the intraspace and interspace scattering length, respectively, given by these two quantities here. So it's given also in this way, this term Gij in terms of the scattering length here. And here is the mass, reduced mass of the system. So the laser steering is represented by laboratory frame time-dependent elliptical trap perturbation in both X and Y direction, given by this format. We have a small quantity here that perturbs the trap with epsilon, and times this in with some frequency here of the steering laser, and with epsilon also the strength. That's follow also some old paper also by Parker and Adams in 2005 about the emergence and decay of turbulence in the steered atomic back system. They have done also for single system at that time. So with polar coordinates, I can write in a more easy way also to see the steering potential. That we have a potential R and theta here, and this is just the trap, and this is the perturbation that I have. So the very small values of this here, 0.025 that we are using, is just to maintain the condensate with an approximate symmetric shape. So it's a very slight perturbation that we keep for the long time evolution. And the laser steering is more helpful to rotate back with values greater than the frequency. In our simulation, we have used this frequency here now for this omega here. One close to one, but a bit too far. So in general, quantum gases are compressible fluids, such that their corresponding density can change when submitted to a force. This is true to a certain degree, as part of the fluid can behave as an incompressible fluid, similar as a liquid. In our present case, the condensate is submitted to a time-dependent steering potential associated to a torque, which is mainly due to a part of the rotational kinetic energy that we can call as the compressible part. So for each component of the mixture, we have this total energy given by this expression. Just a minute. Where this n here is the density, and the time-dependent density that we pointed out here. Is Ni and Nj for the two systems that are coupled. That is the energy that we have. With the current densities in terms of the respective densities and velocity fields, we can write these velocities in this format here and associate the kinetic energy given by that form here, where K stands for the kinetic energy. So this I can decompose now in compressible part and incompressible one. For the decomposition, the density weighted velocity field is given by that form here. The density and velocity here can be split in incompressible part, satisfying the divergent equals 0. And the compressible one, whereas the rotational of Ui, compressible here, is equal to 0. So therefore, with U given by this non-compressed plus the compressed one, the corresponding kinetic energy can decouple in two terms here, that they can separate in the non-compressible and compressible parts. So in two-dimensional space, with this K, the X and Kf, I have this format here, and I can transform that energy, the time-dependent energy, in this format using, in this case, the Fourier transformer. So both compressible and incompressible parts are used to verify the result, the sound waves and vorticity produced by the dynamics. So the torque experienced by the time-dependent steering potential can be obtained through this operator here, the torque that I put also in the polar coordinates, given by the simple expressions here. So corresponding to a rotation in the elliptical time-dependent part of the potential with this transformation here. So it follows the expected values of the induced angular momentum and time dependence and the respective moment of inertia. So in that case, I have LD given this format here, and I can, in that way, associate with some classical rotation velocity, time dependent in this format here. So the rotating frame velocity field at a given frequency omega, given by that here, and the associated particle current satisfy the continuity equation. So the time dependence of the densities and I here, and here is the current here. So when considering a rotating frame at a given frequency omega, I can rewrite that energy in this format here again, using this Fourier transform, and in this term I have also corresponding the momentum space energy, which defines the velocity power spectrum density in K space. Okay, so for computation of this power spectrum here, there is a Bradley and group also. We have developed some codes also just calculate this inside of. And here are some results that I have on this part here. First, for example, because you can see also the long time that you take for rubidium and cesium mixture. So we start with simulation here, and here's about T equal 200, and it goes to very long time evolution to 27,000 in this case of mass imbalanced system, where this is much larger than this. This is for the first component. The first component every time is the lighter one, and the heavy one is this one here. And you can see here that it goes through some region here first, and where it starts to have some turbulence in this part here, with some formation of vorticity around in the border. So, and after a long time interval, they crystallize in some kind of format of vortices inside here, in this format here, where you can see clearly and stay more or less for a long time in this way. Okay. Here, to reach this way here, we take this time here 27,000 in the all units of time. And A2, also you can see more vortices due to also the size of this, because we have a larger mass for the cesium. But again, also we have a crystallization here after passing for this time evolution of this mix. So the upper frame is for the rubidium, as I explained to you, component 1, and the lower for component 2 is cesium. And these are the scattering length that we are using. As you see, as a miscible configuration for this, because I have this one is smaller than this, the interspecies. So I have in a miscible configuration because it's much easier to see some effect of this, the mixture. And here are the corresponding energy that I show here, the binary rubidium and cesium mixture. And here you can see the kinetic, the total kinetic energy. And here is the separation of the compressible and uncompressible one. And here are the two kinds. The second here, the massive one is this line here, and the other is this one here, okay, for the lighter one. And here you can see the compressible with the non-compressible. As we can see here, the non-compressible is this with a triangle. It's going in more stabilization than the other one that's going increasing the sound wave. It's go all way increasing, and the other one there is some bending and go to some stabilization. So the time evolution represented in lab frame for the total kinetic energy and corresponding compressor and incompressor, indicating that way. So the evolution is shown in still stable vortex patterns we can verify. And this we can verify also the other quantities that we have, like the torque for the rubidium cesium. Here you can see also the red one is for the rubidium, or sorry, for the cesium, the heavy one, and the other for rubidium, the light one. Okay. And here is the time evolution that we have. There's some stabilization here. The heavy one, I think it goes a bit up here and stay there. But totally stable vortex are verified. And here what we have here is the angular momentum obtained, as I showed before in the expression that we call the classical rotational velocity for the rubidium and cesium, that you can see also. This is some average quantity, but what we have here is the second component, the heavy one, and this is the light one. As you see, they are stabilizing some kind of plateau after some time, after a long time here. So in that case, you can separate more clearly also this region where this vertical line, more or less, are approximately separate the 3 time intervals of the evolution. First, we have a shape deformation, this part here. Second is a turbulent region that we can call turbulent, and we can verify really if they agree with some kind of classical turbulence with vortex nucleation at the end, destabilize in the region 3. So that this line here is an average of these two. Because why we are doing that? Because we want also to compare with direct rotation of the trap, for example, what happened. Here, for example, I have shown before some results that I have with the steering potential. These are with the steering after a long time. So that I have the crystallization of A1 and A2 in vortex here now, okay? And in the other case, if I replace this steering potential, make this transformation here in my original equation, I remove the steering potential and I replace just by a rotation of the traffic here, angular momentum directly. So just to compare more or less if what I showed before here, there is some correspondence. For example, here is between 0.6 and 0.8 that stabilizing this rotation. Yeah. And here you can see that more or less at this point here, I rotating directly the traffic. I have this value corresponding to this steering mechanism. So that, but of course, there is a time dependent. So you have to take some average also for some interval of the time. No? Okay. But here, for example, you have a time dependence then. So some average, some schema have to be found, take some average of this, some interval of time that we take from the almost beginning then and start. Here is the set of log scale plots for the incompressible kinetic energy spectra for different time intervals here versus this is the healing length that's different from one part and the other part due to the mass. No? Okay, so why these lines here are sometimes that correspond to slightly different position. Here's the wave number and K is the healing length. The spectrum is calculating rotating frame with the upper panel for the first component and the bottom panels for the second component. So I have here the large interval here and the other interval here. I think is already losing some of the behavior that we had before here. For example, here, this line here represents the behavior k to the -3 or k to the -5 divided by 3. That's the Kolmogorov law that we are expecting to see at least in some interval. No? And this you can see from here. This is the line here. Here also, maybe within this interval that we can see some. For that also, we introduce some average kinetic energy spectrum from turbulent regime in compressed kinetic energy spectrum is for the rubidium cell obtained by average over 50 samples in the turbulent time interval that I showed before. Confirming the Kolmogorov that k to -5 divided by 3 power law behavior. This one here. No? Opa. I went down quite a bit here. Here. Okay, here after it moves to another power k to the -3, this interval here. After k time healing length equal around 1 here. Okay. I think just a moment. So here is I have the second case, rubidium 85 and rubidium 87. So these mixtures, they have a mass imbalance very slight. So it's almost the same mass for many effects. Okay, so I can get like some similar picture for 200, 2,600, and 35,000. And here you can see also the turbulent region that start appear here, and vortex come inside of the condensate here, and after crystallizing. So the time evolution of the density, so the first component is the upper one, and the component 2 is the lower one. The parameters are the same as I used before to the other set. Okay, so all the parameters are the same. One thing that we can notice already from this here, and that one I can get some crystallization already established in the last time, 27, something like that. I have already some patterns forming. And here I have to go a bit far. That's also the same that I showed before, but now for this rubidium and rubidium mixed. So I still waiting here just to see the behavior. This more or less only this small interval here. And this for this time here. This for 4,000. And after it loses this kind of behavior. You know? So this pattern is calculated with the upper params. One for the first and the other for the second component. Again, I take some average and kinetic energy spectrum of this turbulent region. CD compressed by kinetic energy spectrum for the rubidium mix by averaging over 50 samples in the turbulent region here. So this is the behavior that I can say that more closely. And you can see that are very similar because the two systems have almost the same mass. Okay. So in conclusion of this part, I have a vortex part produced dynamics by time-dependent elliptical laser steering, together with associated turbulent flow behaviors are studied and analyzed by considering two kinds of mass imbalance coupled boson condensate with an effective two-dimensional pancake-like geometry. With a different mass imbalance coupled systems like this are considered, which are easily accessible and controllable, I think, in actual cold-out experiments. So different regimes that occur in the time evolution due to laser steam are analyzed using the kinetic energy spectrum. So the first stage is the shape deformation introduced by the steering potential. This is followed by a symmetric braking turbulent regime in which vortex nucleation start to be generated at the surface of the two species, which agrees almost with this law of Kolmogorov in some interval of momentum there. A final regime in the time evolution is verified by the production of a stable vortex pattern associated with the summed rotational frequency of the steering potential. As a perspective, the presentation for coupled condensate under steering potential can be extended by using damped Gross-Pitaevsky analysis, because there is no damping in our formalism here, no? With the treatment of the condensate with their corresponding thermal component. It can be useful to calculate precisely, for example, the effective rotational velocity of the thermal cloud. So for more details on this work, I think I have this work that recently appeared here with an assay, a student I have here, Kumar and Bradley from New Zealand, about vortex generation. What is here is just what I just mentioned before, but what we have done, that we try to reach this, that show that this kind of Kolmogorov behavior we can check in this region, and that will go to the K to the -3. Okay, now I move to the other part, my seminar here, about the dipolar system under periodic moving obstacle. This is quite different, the time-dependent potential that I'm using in this case. So we are investigating dynamics associated with moving Gaussian obstacle in pancake-like trapped dipolar back. So it's a single condensate, dipolar condensate, and I followed leading to quantum turbulence and vortex production. So by solving a non-local to the Gross-Pitaevsky formalism in real time, the critical velocities for the nucleation of vortex dipoles and vortex clusters are obtained with respect to the dipolar interaction strength. So that's the usual formalism with this dipole interaction. That is our trap here and the 3D, the nonlinear part here. In 3 dimensions, this is the equation here, where I normalize in this way. N is the number of atoms, and AS is the S-wave scattering length, and this is the strength of the two-body contact interaction, with UDD being the dipolar interaction. So the trap will be assumed with a pancake-like cylindrical symmetric harmonic shape, as usual, perturbed now by a Gaussian-shaped time-dependent interaction. In this way, so I have the harmonic oscillator here, and after I have the trap, the Gaussian format here, where this is the use of the in 3 dimensions, this one that where I use this lambda much larger than 1 to simplify also the formalism, and we can come to a kind of pancake-like again formalism. Okay? So the Gaussian to the periodic time-dependent obstacle as a perturbation to the traffic. It's written in this way, where this is the width and the amplitude here. And that is the time-dependent notation here. The obstacle is moving a circle with the radius epsilon and frequency nu here. That you can call also velocity of the. So in polar coordinates, again, also I can write in a simplified way, also in that format here. That is the radius of this, and this is the usual radius of the two-dimensional. And as you can see, also you have this angle here changing in time. So that's the dipole between the atoms A1 and A2. In general, J, you can say that. And with their line vector, make an angle theta related to the z-axis, and that we can take alpha theta around 90 degrees, right? For a strong pancake-shaped trap. Both dipoles polarized in the same direction make an angle alpha, we call tilted angle here, with respect to the z-axis. There are also things right in momentum space there. Picture there. So the tunability is performed by time-dependent magnetic field with dipoles rapidly rotating around the z-axis. The magnetic field is given by the combination of a static part along the z direction and a fast rotating part in the xy plane, where with frequency such that the atoms are not significantly moving during each period. Once perform a time average of the dipole-dipole interaction within a period, the 3D average interaction between the coupled dipole atoms with magnetic dipoles are given in terms of the Bohr magneton. Here can be written so in this format here. That's the general here, but after with just one angle, just taking theta equal 90 degrees. So with the frequency and the length units given in these usual units of the trap. And I have this written that dimensionless format, and the three-dimensional equation is given in this format here. But dipole interaction is this one here. And this is the cubic term. This is the units that here. And how, as I take a lambda very large, so I can separate the movement in Z part from the other part here and integrate this in Z. So the 2D reduction of the dipole-dipole interaction configuration space is given by the Z integration. In this format here, followed by a Fourier transformer to the moment space of the dipole-dipole interaction and density. So both are taking the Fourier transform. The configuration space integral is related to the corresponding inverse Fourier transform. This is in detail in this paper here. So that's the corresponding passage from the inverse of Fourier transform for this quantity that was previously obtained and the Fourier usual Fourier. So here in the 2D moment space, the dipole can be expressed as the combination of two terms, considering the orientation of the dipoles, alpha and projects of the Fourier transform in moment space. One term is perpendicular with the other parallel to the direction of the dipole inclination. They are respectively given by this format here in terms of the air function here, the complementary air function. As K is in this format, by considering that all directions that are possible for a polarization field rotate in this plane, we can also average this by replacing this term to K squared divided by 2, and in that case, it comes in this format by combining the two terms. I have the potential in that format, and the total 2D momentum space, dipole-dipole interaction can be written in a simple form, combining both. With dipole term written in the Fourier space, the effective velocity types two-dimensional dipole back is given in this format here, and this is the term that I have also calculated using the Fourier transform. So this is the two-dimensional wave function normalized to 1 also, and the GS is in terms of the scattering length here. Now through numerical simulation, solution of this equation, we investigate the vortex nucleation. For that case, we use the algorithm Crank-Nichols method with fast Fourier transform. Really, I have to say also that most of this calculation is being done now by Sabari, one postdoc that we have done is doing most today. These are part of the calculation. And these are the kind of, this is taken just to represent where is the potential, not the real picture that, but just the kind of thing that we are playing around. The main system that we have make is this one and this one here. So rotating this format here, the impurity that we have, the Gaussian potential, or this one. This one we have played a bit of, but it's not giving too much difference of what the main ones are this circular and this one here. We have said these types of motion of the Gaussian obstacle. So I'm going also to show the case of 1 and 3, in which the amplitude of the obstacle is kept fixed. Because in this case here, the amplitude is not fixed. There's some periodicity that I can put here, but these two are kept fixed. In case of 2 and 4, we have verified the effect of small vibration in the amplitude. So this is our phase diagrams of the critical velocity. So you see this part here, by moving, this V represents the velocity. And this alpha is the tilt angle that can decrease or increase the dipole interaction. Remember that in the way that's written there, this dipole interaction, when it's 0 is the maximum. So it's maximum the effect of the dipole interaction. And after it's going to decrease till one point here where it changes the signal. Because for 54, I think, is the magic angle where it changes the signal. But I'm representing most of this part here. We have also result for the other part when it shrinks, because effectively this dipole interaction is acting together with the other interaction that we have. So it's really, in fact, when I go to negative, it's just reducing that. So it's reducing also the size of this. So it's more difficult. So we have to be careful in taking the radius of this perturbation, this Gaussian perturbation. So here is, so I have for the case 1 and the case 2, the results here now. This is the case 2, where you see also the region that we have vortex goes more to the right hand. And here I can have vortex in less point here. And this is the case that we have a movement only in one direction. So when I have an angle theta equals 0, I have only in x direction. So this is the regime for vortex emission. I start to have vortex emission here, and after at some point here, this emission of vortex not coming anymore as a pair, but it comes as a cluster. So that's more or less defined in this way. And that's the parameters that we have for the scattering length in terms of Bohr radius, and for dipole-dipole interactions, and the number of particles, and also the potential, the A0, the strength of them, and the absolute 0.5. So this is crucial if I reduce too much the size of the condensate. So I have to decrease also this epsilon. Here are some results that I have for the case of circular movement, type 1, with the speed 0.8, this one here, and 1.5. Considering a short time interval here that I have. I have only to this part here. And can you show me the GIF also? Okay. It is more or less just a picture of a movement, what we have if we have low speed and high speed, how it creates this vorticity. It comes as pair, but one comes before the other because of the geometry that we have. No? And here when we have a high speed, like a V 1.5, and that is the time that we have here. Okay? Oh, so that's it. Okay. I hope it's okay. Thank you. And here is just representing static this movement here. I can also show more pictures here if in a long time interval, but as you see here, if I have a low speed, I can keep for long time also this kind of density, you know? With this, of course, this point here is the point of by obstacle, no? That I'm moving. And the others are the vortices that are being created here. And here, if I create here, for a long time here, decreasing a lot these densities, no? So it is better to see in the small intervals for large velocity. No? It's collapsing there. And here is also a time evolution of the vortex nucleation for type 1, also the same circular, for 3 different speeds, 0.3, 0.8, and 1.4. No? Alpha equals 0 is when I have the maximum. Oh, sorry. Here. When the maximum effect of the dipolar interaction. So you see here the time is given here 0 start. Of course, when it's 0 here is before putting the impurity inside the Gaussian obstacle, and here is already with the Gaussian obstacle, and after how it creates this vortex inside here. So here I say when I have here the as shown also in some diagrams there, you start having more than a pair every time creating here in this movement. Here is the case of linear obstacle, when I have the same speed, for example, 0.8 with alpha equals 0 in the upper line, and 1.5 in alpha equals 0 degrees, and 30 degrees in the other two cases here, 0 and 30 degrees. So this means that when I have 30 degrees, I'm reducing a bit also the effect of the dipolar strength interaction by the cosine alpha that I have. So here I have the nucleation here, but one thing that you can see more clearly, so why I think that this case is maybe to study I think analytically in some way, because you can see the creation of pair every time symmetrically, just because the movement is in just one direction. And here also you can see also how it comes symmetrically. So that I have I reached almost conclude. I have some other pictures also to show about the energy and so on, but I think that this correspond is the same as the previous case that I showed. Okay. So when I report under periodic moving obstacle, we report some preliminary results on this dynamics of vortex in a dipole back by solving numerically the 2D non-local gross potential equation with the trap perturbed by a moving periodically obstacle. So the critical velocities for the formation of vortex pair, as well as to produce clusters of vortices, are shown that increase by increasing the strength of dipole interaction. When I say increasing the strength, again, I'm just remembering that I increase the strength, diminishing the angle alpha. Opa. Be careful. Okay. So for the formation of what, as well as to produce clusters, are shown that increase by increasing the strength of the polar interaction. So for the thing dynamics of vortex and radiation of pulse, unit dynamics of vortex with opposite rotation. Okay, just as some related reference that I have here. One is that published recently also by Bradley about the numerical methods also that they have used for the spectral analysis. There. And this one paper that gives this motivation was to study for the coupled system by Parker and Daniel. And after I have some other papers here also, that people also come here also, they have some physics report to study more this turbulence in trapped atomic Bose-Einstein condensation. So in that case, I have just finished my presentation. Thank you very much.
Okay, thank you very much, Lauro, for this very nice presentation. We have plenty of time for questions. So yes, Nick. All right.
Hi, thank you for this very nice talk. I'm just a bit confused about something, but maybe it's my mistake. So when you have a condensate and you induce these shape oscillations, you know, you're trying to crystallize into a vortex lattice. you call this initial regime turbulent when you're exciting these surface modes, basically. And it's typically one vortex, one by one, that comes in
Yeah.
from the lattice. I naively would not have thought of this regime being turbulent. I thought that turbulent is a slightly different regime, unless it is in the sense of somehow sort of wave turbulence, but then I don't know how wave turbulence leads to this formation of the vortices. So could you explain a bit this process and why you call the early regime turbulent?
Yeah, this I'm just really I'm not a theoretician that came not from this turbulent area. So I just trying to follow also the way that they try to analyze this regime, some interval, because also Bradley was saying that maybe the time is too short there to conclude that really a Kolmogorov behavior. That's really is something that I really have to learn a bit more about that. So really, because you are saying that, for example, why we are calling already turbulent now. So I'm just following something you studied that was we are trying just to see this spectrum in this interval where is not crystallized any vortices still. So there is only some noise there that you can see. We are trying to separate, and also we have to remember that we have also the sound waves and also these other together. This
Of course, no, it is quite a dynamically moving system.
Yeah.
But I'm just unaware. I mean, have other people claimed this to be a turbulent regime early on, or is this the first claim of such?
No, I think it's not the first claim. I think there is also you can see also the people by not by
the Parker and Adams.
Bradley also there some recently where they claim, but it's for a single condensate there.
Yeah, but so this early regime they still call turbulent before the.
Well, so but
okay, thank you.
Not sure. Thank you. Thank you for the.
Yeah, concerning to the Bose-Bose mixture, when you have these vortices, I'm wondering if you can see that one species go into the core of the second species. So in other words, if you see what is called massive vortices, because it's expected that in some cases in the Bose-Bose mixtures, when you rotate one species, the other species go in the core of this, and then the vortices become massive and somehow the dynamics could change. Could you comment on that, or have you seen this?
I really, this is something that will be think because you say that are combined with that, because you have two species there, and how to have that really are in the same trap now. That's the, and that this is some question that I think
normally. So imagine that you put a small fraction of a second species.
Yeah.
So it was made, for instance, in helium with hydrogen. These impurities go normally in the core of because these impurities do not participate of the angular momentum of the rest. So they tend to go to the core because the core is less dense. Then they try to go there, and it's one of the ways in which you can follow a vortex. For instance, in helium is the only way. Because you have a vortex, you cannot see the vortex unless you put some impurities. In the more popular cases, when you put hydrogen and the hydrogen go on the core, and then you can visualize the hydrogen and you see the vortex tangle and the. I'm just wondering if you can, because I think that if the vortex has a mass or not, in the sense that you feel the core or not, could affect the dynamics in general.
Yeah,
it's an observation.
Yes, thank you. But really, this is something that we still analyzing, and also any kind of question like this, I think can be important for in our analysis to check better, because not just some preliminary also that you understand. And really, this because you see that this second case that I shown here, it comes more dynamically. This the production with just some kind of okay, thank you.
I have actually a follow-up question quickly before. So on your slide 24, where you were showing these patterns of vortices in the two different species, I mean, it was quite striking that it seems that the or 28, 24, exactly.
Okay.
So my question is simply, are the vortices of the rubidium sitting at the maxima of the distribution in the cesium. So it's basically, is there a correlation or an anti-correlation between the two images on the right?
The two images. No, because in numerically,
it's a mixture, right?
yeah. Yeah, but there is some correlation because you can see, but only that is the lower that you can see below. But more or less, when you have that hole in some place there, where the vortices, the other is in, should be in another position. Just in principle, this.
But that means there is some correlation between these two patterns, and can you also inject less vortices such that you give more space to the other? Somehow now it seems like you only allow.
But this I think is quite difficult because you have to restart the program again because it takes a long time also for this reaching. So, and also to get some kind of vorticity here, looks that first we have to explore the kind of frequency that we can use to create this kind of turbulence, dynamics that end up this. And it was tried also before by Kitchen to have some smaller frequency to see, just to reduce. But it stay before 0.9, we cannot get any kind of vortice again.
And one additional question: can you say something about the vorticity? So are they all rotating clockwise or counterclockwise? So I'm wondering.
No, this I cannot say. Because this comes from some dynamics that we can see only the vortices there crystallizing in some position after a long time. Only that they are not moving these vortices. They end up.
Okay, thank you.
Okay.
We have one more question.
So, hi, you showed some results for binary mixture, quantum turbulence. So if we consider a system where the spin dynamics terms also in the system,
what?
Spin mixture terms, spinor condensate, let's say. So then also can we expect this Colgrove power law, I mean, Ks over minus 5/3, or it would it not be there?
I don't know because you're just taking some other effects to see this Kolmogorov, but I just not clear. It's can be.
Okay, sir. And other thing is like what are the application of this quantum turbulence in like experiments if we study that?
Yeah, this is what we expecting because we are doing some kind of simulation that we expect that experimentally one could see something similar actually. Because notice that in this case here, we are just disturbing spherically symmetric, but just slightly. So why it takes a long time because you don't, if we start shaking too much here, we becomes difficult to any kind of analysis. But so in this way, what we are saying that maybe one should try also to do very slowly this deformation elliptically, and to see if this kind of effect can be seen.
Okay, thank you.
Okay, are there any further questions? There is one.
It's more a suggestion than a question, because at some point we have discussed also these quantum fluctuation corrections to the Gross-Pidevsky equation.
Okay.
They are not necessary here to describe something, but they come the reality a little bit closer. And as we know from nonlinear dynamics, tiny changes can have in the long time some effect. So I'm wondering in the context of quantum turbulence in general and maybe these particular scenarios you have investigated, how robust they would
that would be very interesting.
In connection to including those quantum fluctuation terms, which are known for the Bose-Bose mixtures as well as for the Daimler terms, right?
Yeah, sure. For instance, sure. That would be very interesting to introduce already quantum fluctuation and just try to study this because it's just a small perturbation that we have. That we try also this is by potential there in this, but we could have already there in the nature that we have so this kind.
Okay, do we have any further questions? I might have one actually looking at this slide. So you choose to have rubidium and cesium, and then you write that you have very comparable scattering lengths. Actually, it's 60 and 30 A naught.
Yes.
Do you have any comment on what would happen if I have a species where I have, for example, a Feshbach resonance, and I can make the vortices extremely tiny with strong interactions, controlling the healing length?
Really, the idea to use this is only to have a mixable configuration, only that. But we could choose another value, of course. But
and that would change your. Have you?
No,
so you have just done these simulations for these parameters.
No, but we have not done for a long time. I think at least I don't remember if you did also. It varies more these terms here. But I guess I think we are getting the same kind of thing, maybe more time or less time that we can have this kind of final picture. But that I'm not sure, because this, at least if I take this smaller than this, much smaller, it happens that we have separated more the symptoms, so we cannot see this effect.
Okay, thank you very much. So if there are no further questions, first of all, let's thank all the speakers from this session this morning.
Thank you very much.
And since we're already giving a round of applause, I think we should also thank the organizers of this workshop for this excellent conference. Yeah, Axel and Arnaldo, thank you very much. And I just hand over the microphone now to someone.
Oh, the homepage. A little bit reduced, but I was told that, for instance, the van which brings our Sakalos people back to their home, that they have installed some video screens, and they have been following Laurio's talk and also are following the concluding remarks. So greetings to the Sakalos shuttle here from the lecture hall. So we have had 18 invited speakers, 19 posters, and then of the order of 7, 8 other participants. And among the students, there were 5, 6 very courageous students insofar because they attended also prior to the workshop 2 weeks school on ultra-cold quantum gases. So they are now very well trained after having 3 weeks of talks and discussions and experiences. Now, I think it's also time to thank everybody who was involved in this business here. And the first thanks, I think, should go to the late Mahir Hussein, because he envisioned many years back, so to speak, today's event, and he managed to get the financial support from the respective agencies. And it was both Arnaldo's and my intention to try to follow, so to speak, his spirit in this kind of conferences. And I think having a crowd of people of about 45, which is not too large so that it is not possible to talk to everybody, and not too small so that there would be no further discussions, right? I think we had a quite number of participants just in between these boundaries. Now, the funding agencies are also seen here, right? So we had funding from the Sao Paulo state by FAPESP, then from the ICTP, which has a South American dependance, which is called SAIFR. Then there's UNESP, which is
a university, if I understood it correctly, funded from Sao Paulo state. And then IFT is presumably the Institute for Theoretical Physics belonging to that university. And then most prominently also the Instituto Principia, because they gave us the possibility to have this meeting here in this quite nice lecture hall. Then I should thank also Arnaldo, who is hiding here for a certain purpose at the side. So because, you know, the funding was there, he was a perfect local organizer. So from my side, as a foreign organizer, there was quite not too much to do apart from enjoying the whole event. So I think he brought the spirit of Mahir Hussein, so to speak, to this event. And believe it or not, he helped with a great routine, as if he would have organized already a lot of conferences. So it was really a pleasure. But I think we should also thank the people behind the scene, whom you have only partially seen. And we have here Jandira Oliveira and her assistant Natalia. Maybe you come down, because you know, they produced this electronic booklet also with the help of Umberto Neto from SAIFR. So this was a lot of work. And then they had with everybody of you some more or less extensive email correspondence to serve all the particular individual needs of everybody. And I think it was very pleasant to stay here, because it was a workshop of the short ways, right? There's the hotel, there's the conference site, a lot of restaurants, vibrant Sao Paulo. So I think it was a great location here, and you helped to make it possible. Thanks. And as you have may noticed, from time to time, there were some young people running around helping here technically, and they even exchanged from day to day. So I was told that Wellington, Juan, Eduardo, Milena, and Luis helped during the whole week. So I think we should then also give a hand of applause, because that was quite essential at moments where we thought, oh, something is happening here technically, but they happened to solve all the problems. So finally, I think I had the impression that this field of low-dimensional quantum gases seems to be a quite vibrant one, right? So we had a fair cross-section of the field, I think, with atomic and photonic realizations, with all kinds of numerical and field theoretical methods being applied. And I'm looking now to Arnaldo. So maybe in the not too far future, we may think about of having a similar event, maybe because things are ongoing, and it might be worthwhile to meet in this circle again. And at the very end, because it may be very long until this next event, I have some self-advertisement. Can you show the next slide, please? Yes, exactly. So at the beginning of August, from the 6th to the 12th of August, we will have a Barton Physics School on ultra-cold atoms and molecules. And if you please scroll down a little bit at the homepage. Yes. So down so that we see all the names and topics. Yes, exactly. So we have already 7 invited speakers who agreed to come. So you can see the topics. So there's about, we have Nathan again, right? So that's very great. And then we have other topics, BAC, BCS crossover, quantum gas cavity QED, Rydberg physics, and topological pumping, Floquet engineering. So I should say that if you attend, there is some tiny school fee, and if you would be able to arrive with some by some means, this event would be for free lodging and accommodation and meals, right? So it might be nice to see you then in August in Germany. And with this, I thank for your attention. I think we can now enjoy a 1 meter snack, I was told.
Wait.
With, please note, not alcoholic drinks. That was made very clear right from the beginning.
No, he's asking us to take a last picture here in
Oh.
front of the stage, please.
Good.
Anyway, you must come to downstairs and we take a